Okay, I think that's now a pretty good crowd of people, so we can go ahead and get started. So it's a pleasure to have Michael Abdul-Masih as our lunch speaker today. So Michael is an ESO fellow at Paranal, and he was just telling me that he actually moved to Chile last year in the middle of the pandemic, which has probably been an interesting experience, I guess. So prior to that, Michael got his PhD last year in 2020 from the Institute of Astronomy at KU Leuven. And his research focuses on spectroscopic studies of massive overcontact binaries. And that is what he's going to tell us about today. So please take it away, Michael.
Thank you very much. Thank you very much for inviting me to come speak with you all today. Very much looking forward to telling you about the stuff that I've been doing, and I've already had a couple of very interesting conversations earlier today with some of you who are in the room. So thank you very much for that. As you mentioned, my name is Michael Abdul-Masih, and I'm currently an ESO fellow in Chile. And today I want to talk to you about some of the research that I've been doing during my PhD and also that I'm continuing now on massive overcontact binaries. And I've titled this talk, Massive Overcontact Binaries, a Fork in the Road of Massive Star Evolution. And I hope that I can convince you today of how important the massive overcontact phase is in massive star evolution and why it deserves as much attention as we can give it. So before getting into it, let me first define my terms. Depending on who you ask, the definition of a massive star can change. When I say a massive star, I'm talking about stars that will end their lives via a core collapse. So I'm talking about stars that are more than 8 times the mass of our sun. And these stars are dominated by their strong stellar winds and their high UV fluxes. And these allow them to really drive the chemical and mechanical evolution of their host galaxy. So here I have an image of the Hubble Bubble. And what this is thought to be is the interaction between the stellar winds of a massive star and its environment. So you can really see kind of the effect that it can have. So by understanding better how massive stars spend their lives, how long they live, how they evolve, it allows us to better understand the environments in which we find them and how they affect their environments around them. So one can't talk about massive stars without mentioning binarity. We know that a majority of massive stars are found in binary systems. As you start getting to the upper end of the HR diagram, this percentage of binarity turns out to be very close to 100%. And these binaries are often found in very short orbits. And we expect that about 70% of all massive stars will interact with a companion at some point during their lives. And these interactions can change the evolutionary pathways of these stars quite a bit. Now, of these interactions, you can have things as simple as, I say simple, but things such as envelope stripping, but you can also have mergers. And I'm going to be talking about, I'm going to be focusing on the mergers in this talk. So before the stars actually coalesce, they go through an overcontact phase. And we expect about a quarter of all O-type stars to go through this contact phase. However, despite the fact that so many stars are expected to go through this phase, we know very, very little about it. This is because there's many simultaneous physical processes that are happening in the interiors of these stars that really muddy the waters. We have mass exchange, tidal locking, we have mutual illumination, internal mixing, angular momentum, transporting momentum loss. And all of these things lead to very big uncertainties when we're looking at the evolution of these overcontact systems. That in combination with the fact that we have very few or very limited observational constraints on these internal processes means that we really don't understand much that's happening in these systems. For example, we only know of about 10 O plus O overcontact systems. And of these 10, only about 3 or 4 have been studied spectroscopically in detail to the point where we have an idea of what the surface parameters are, let alone what the internal parameters are. So despite the fact that we have very little observational constraints, these mergers and the overcontact phase have been used for many different kinds of evolutionary paths. By adjusting the parameters that you have in your models, because as I mentioned, these have very, very large uncertainties. Depending on where you decide to put that each of these parameters, it can really change the outcome that you get for these systems. So for example, massive overcontact binaries have been postulated to form magnetic massive stars. So in this case, the magnetism originates due to shear instabilities that develop as an accreting star accretes matter from its companion. And in this case, there are 3 plots here. This is from Fabian Schneider's 2019 paper. And this is 3 different snapshots. And in color, you're seeing the magnetic field. And what happens is as the donor star begins to transfer its mass to the accreting star, shear between the accreting star and this stream causes a magnetic field to begin to generate. As more mass is transferred, this magnetic field becomes bolstered. But then, really, when the cores end up merging, the shear between the cores is very, very strong, which causes this magnetic field to bolster. So, this is one possible outcome of massive overcontact binary evolution. They can also form OE or BE stars. These systems are characterized by their very strong emission lines, as well as their very broad spectral features, which is thought to be due to the fact that these stars are rotating at near critical rotation. The emission lines are expected to be coming from a disk, and one way that you could form these stars is due to a merger. So as the stars get closer and closer and closer, and as they eventually merge, you get this very, very high rotation, which can lead to perhaps rotation that is above critical, which leads to a decretion disk around the star. They've also been theorized to be able to form LBVs, luminous blue variables, which then go on to become superluminous supernovae, as well as blue stragglers. So in this case, we know the cluster turn. If we look at a cluster and we look at the HR diagram, we have an idea of the age of the cluster based on the turnoff. However, we find often these stars that are in a region of the HR diagram where we expect them to have already evolved and evolved off of the main sequence. One way that you can explain these is due to stellar mergers, where you have 2 smaller stars that live obviously much longer than the massive stars that merge and create a more massive star that has lots of fuel fresh for burning. Additionally, it's been postulated that these overcontact binaries can form gravitational wave sources. So we have a whole bunch of different outcomes of this that go through this overcontact phase. But the real question is, what really determines this final fate? How do we know whether a massive overcontact binary that we're looking at will end its life as a BE star or a gravitational wave source? These are very different kinds of objects. And while there are many different processes and many different aspects that you would need to consider to answer this question, really what we're going to be focusing on in this talk is internal mixing. And I'm going to do a very big oversimplification, and I'm going to break these up into 2 separate groups. We have the evolutionary channels that result from inefficient mixing. You have the BE stars, the LBVs, the blue stragglers, and the magnetic massive stars. Then you have the evolutionary track, or the evolutionary paths that result from very efficient mixing, the black hole plus black hole sources. And this pathway down here is one that I've spent a lot of my PhD life investigating, and this is known as the chemically homogeneous evolution pathway. And it was first proposed as a way to form black hole binaries in 2016 by 3 papers that came out at just about the same time. And then more recently, in the past 2 years, there's been a couple of updates now or a couple of studies looking at this pathway in a little bit more detail, now that we have more observations from LIGO Virgo to update this. So as I mentioned, this relies on very efficient internal mixing. So how exactly do we get internal mixing? There's a couple of different ways. Let me start with this one. So as a star is evolving, what we expect, what stellar evolution tells us, is that its core should contract and its envelope should expand. Now, due to conservation of angular momentum, as the core contracts, it begins to rotate more rapidly. And as the envelope expands, it begins to rotate more slowly. And this differential rotation between the core and the envelope leads to shear instabilities, which cause eddies between the core and the envelope. And this allows you to bring material from the envelope into the core for burning, and vice versa, material from the core to the near core envelope region. This is very important because this allows you to extend the life of your star as you're bringing fresh material from the envelope and fresh fuel for burning, which can have quite a big effect on the evolution. The next process that I want to talk about relies on the fact that these stars are not spherical. So we know that rotation plays a large role in massive star evolution. We know that a large number of these stars are rapidly rotating, and the rapid rotation causes these stars to deviate from spherical symmetry. As well, so does the stars that are in close binary systems, such as overcontact systems. And these deviations from spherical symmetry lead to changes of the surface parameters across the surface. So in this case, as the star is rotating rapidly, its equator begins to bulge out while its poles stay where they are. And this leads to a change in radius across the surface, which leads to a change in surface gravity across the surface. And from the von Siepel theorem, a change in temperature. So in this case, regions of higher surface gravity correspond to warmer temperatures, and regions of lower surface gravity correspond to cooler temperatures. And while the star can be in hydrostatic equilibrium and deviate from spherical symmetry, it cannot be both in hydrostatic equilibrium and thermal equilibrium at the same time while not in a spherical state. And because of that, this means that since the star isn't in thermal equilibrium, we have large-scale circulations that develop in the envelope of these systems that bring material from the hotter regions of the surface down to cooler regions and then back down close to the core. These are known as Eddington sweep circulations. And this is a very powerful mixing mechanism that allows you to get material from the near core region up to the surface and mixed throughout the star.